acids and bases. I want you to pay a lot of attention into this unit because it's one that carries through directly into your university courses, and they're going to expect that you have a pretty solid understanding of it. So let's start with talking about what an acid is. So acids and bases kind of fall into the same categories of solutions that we started talking about in our last unit. So a couple of reminders. Solutions can be made with ionic compounds or molecular or covalent compounds. Ionic compounds are composed of positive and negative ions, so they're going to form electrically neutral solutions. Now, think about that for a second. They're made up of ions, and yet the solution is neutral. Why would that be? Well, in any ionic compound, there's an equal amount of positive and negative charges, so technically they cancel each other. Just because the solution, however, is neutral doesn't mean it can't conduct electricity. It just means that the amount of positive charge is equal to the amount of negative charge. We can also make solutions out of molecular or covalent compounds by dissolving a covalent compound into water. Now, if that compound that we've dissolved is capable of conducting electricity, we will call it an electrolyte. Electrolytes are compounds that conduct electric current in aqueous solution or in the molten state. So all ionic compounds will act as electrolytes because there's positive and negative charges available to carry electricity through the liquid. Molecular compounds typically are not. However, some molecular compounds, if they're very, very polar in nature, if they have a very strong positive and negative end to the molecule, actually can, to some degree, conduct electricity. The better the conductor you are, the stronger the electrolyte you are. Strong electrolytes, then, are ones that would readily put lots of ions into the solution and become good conductors of electricity, and a weak electrolyte would be one that would not dissolve into solution and therefore would be a poor conductor of electricity. So suppose we have 3 containers of solutions and we don't know which container contains which. Let's suppose that one container is a solution made of sodium chloride or salt and water. The second container could contain possibly a solution of sugar and water. And suppose that the third of these containers contains hydrochloric acid. How could we tell them apart? Obviously, with one of the containers containing a very strong acid, taste would be an exceptionally poor choice for this solution to be distinguished. So what else could we do? Well, we could build a pretty simple conductivity apparatus by taking some kind of battery, and I've got my little chemical symbol here, or electrical symbol here for a battery, and connecting it to a small bulb, and we could see whether or not the solution would conduct electricity. If we could find out whether or not the solution could conduct electricity, we could separate the ionic substances from the covalent ones. For example, if I put my conductivity tester into the first solution, and we found that the solution lit up, that would tell us that this solution must be one of our ionic compounds. So we now know this first solution can either be sodium chloride or hydrogen chloride. If we tested the second solution and got a similar result, we saw that the bulb also lit up, we would know that the second solution would also be either the sodium chloride or the hydrogen chloride. Testing the third solution then would show that no electricity was being conducted. We now know that this solution here is likely to be the sugar solution. This solution does not conduct electricity. How else could we tell now between which of these two solutions is simple salt water and the other one containing hydrochloric acid? Well, there is a couple of ways that we can test, including litmus paper, bromothymol blue, and other indicators. Let's come back to this in a moment. In your notes, there's a chart that separates between acids and bases. I'd like to make a list of common characteristics of both acids and bases for us to remember. Acids, for example, will turn litmus paper to a red color. They will have bromothymol blue turn into a yellow color. Both litmus paper and bromothymol blue are indicators. They are chemicals that change color in acids and bases. Acids also taste sour, which is why they're commonly found in citrus fruits. They react with metals and produce hydrogen, usually in the form of hydrogen gas, and they have pHs that are low from 0 to 7. Bases, however, turn litmus paper blue. They'll turn the indicator called phenolphthalein to be a pink color, are bitter tasting, have slippery feel, form cleaners, and are at pHs 7 through 14. So, using this information of acids and bases, is there any way that we could tell which of their two solutions contained the sodium chloride and which one contained the hydrochloric acid? Well, if we were to dip a piece of litmus paper in, we would expect the color of the litmus paper to turn red. Litmus paper typically comes in two faintly colored strips. They look pink and powder blue, but we commonly call them red and blue. If we were to dip litmus paper into the first solution and the solution stayed red, it might mean that this is our acid solution, but it also might mean the solution was neutral. If I take the blue litmus paper and also dip it into this solution and it does not change color, then we know that the solution is neither an acid or a base. The solution must be our sodium chloride. If, however, I were to dip these same two strips into the central container, we would see that the red strip, the strip that would change red in acid, would stay red. And the blue strip, if I were to dump this one into the container, we would see that it would turn into a reddish color, which tells us that this is an acid, and therefore this central container would be our hydrochloric acid. So we can use some of the information that we have about acids and bases, but also some of the information about what we know about solutions to determine what is in our containers. Now, the definition of acids and bases that we were just talking about is based on the same definition by a guy named Arrhenius. And this is the definition that we taught in grade 10. Arrhenius said that acids were any compound that starts with hydrogen in their formula, but more importantly, when you put them in water, will liberate hydrogen ions. Bases are any compounds that, if you put them in water, liberate lots of hydroxide ions. So from Arrhenius's point of view, anytime he saw a compound that started with hydrogen, he assumed it to be an acid. And anytime he saw a compound that ended in hydroxide, he assumed it to be a base. Not all substances, however, containing hydrogen turn out to be acids. Hydrochloric acid that we just discussed, when we put into water, readily breaks apart to form hydrogens and chlorine, so it is indeed an acid. But methane, which is an organic molecule that we talked about in grade 10 and grade 11, has lots of hydrogens on it, but these hydrogens do not ionize. They do not fall off the molecule and float around freely in water. Methane is not an acid. In acetic acid or vinegar, even though there are many, many hydrogens on this molecule, it's only this hydrogen attached to the oxygen in a very polar bond that will ionize or fall off. This is an acid. So just because we see hydrogens doesn't mean that the solution will be acidic, and if there's lots of them, it doesn't mean that it will be more acidic. We also have some problems with very common molecules like sodium bicarbonate, which we call baking soda, or sodium hypochlorite, more commonly known as bleach. Both of these are bases. They're bitter, they're slippery, they neutralize acids, but neither of them has hydroxides in them. So even though we're not seeing a hydroxide in the molecule, these guys are indeed bases. And then we've got something like water. Water is composed of a hydrogen attached to a hydroxide molecule. Water can be both an acid and a base. Any substance that could be both an acid and a base is referred to as being amphoteric. You need to practice Arrhenius's definition of what it means to be an acid and a base. I'd also like you to take a look at what it might mean to be a mono, di, or triprotic acid. See if you can find the definition for this in your textbook. Take a look in chapter 18 for that definition and see if you can find an example for each as well. There's also a series of questions that you guys can work at in your textbook in chapter 18. In our next lesson, we're going to take a look at some more general definitions of what it is to be an acid or a base. Some things that maybe take into account some of those common acids and bases that Arrhenius's definition did not include.